Hello, my name is Novalib, and this is my research project presentation. The title of this research is called Complexity Measures for Understanding Machine Learning Generalization. In this research, I will be going over a concept called the Kolmogorov complexity, which is an information theoretic measure for describing the simplicity or randomness of data. And I will also be going over how it can affect machine learning generalization. The goal of this entire research is very simple. It's to answer one simple question, which is why do modern machine learning models perform well on some data sets, but then struggle on others, even if the models are very powerful and complex. Before I dive deep into the rest of the research, I wanted to go over the motivation as to why I chose this line of research. And it's that in machine learning, generalization is the ability of a model to perform well on data. And although we have very large and I'd say expressive and complicated models today, I mean, you could take a look at neural networks and deep learning and whatnot. We still don't fully understand why they generalize well in some settings, but then tend to fail in others. And so, one of the ideas from theoretical computer science uh, that could help explain this is Kolmogorov complexity. Again, it just measures the shortest possible description of a data set, and it kind of follows a simple rule, which is uh, if a data set is random and has no pattern, its description is long. And if it does have a pattern, its description is short. And the key idea is if learning is basically finding a compact description of the data, then simple data sets should be easy to learn, and more complex data sets should be harder to learn. And so I can move on to the methodology. So for the methodology, it's very straightforward. First, we create the data, the different data sets. I created three different data sets, each with varying levels of complexity. The first one is just following a very simple linear function, which is y equals 3x plus 5. The second data set is a medium complexity, and it's a polynomial plus some random noise mixed in. This one has a structure, but obviously with the random noise is going to make it a tad bit more, you know, unstructured, I guess. And then dataset C, which has the highest complexity, has absolutely no structure because it's just filled with complete random values. Uh, so after creating the data sets, I'm going to go over the model training and the complexity estimation. So right here, this small little equation, I guess, is basically just saying that the estimation of a data set is equal to the compression size of the data set. And so it just follows a simple rule, like I said earlier. A smaller compressed file should indicate a lower complexity, and a larger compressed file should indicate a higher complexity. And then for the model trainings, I used linear regression, decision tree, and a small little neural network. Uh, a hidden layer as well. Just one hidden layer, nothing too complicated. And then after we do that, we're going to evaluate it, see the gap, which is going to be the test error minus the training error. And then finally, we're going to analyze it. So let's move over right here. This is my code. Uh, right here, these three chunks of code are creating the data sets. This one is the linear one, which has the lowest complexity. This one is the polynomial plus some noise. And then this one is a complete random one. And so I created these three CSVs. We can take a look right here. A should be right here. This is A, which is complete linear. This is B, and this is C. You can see how this is just complete randomness. And so right here, we are just reading the CSV files, nothing too crazy. We're getting the data sets, and then this is where we are uh, listing out the models that we're going to be using. Right here, the inner regression, decision tree regressor, and the MLP. And right here, I just used 16 nodes. Nothing too crazy, just something small. Uh, I set the iterations to 3000 because it was kind of slowing my PC down a lot. You'll see why that's kind of important right here. Uh, but yeah, right here we're just simply looping over all the different data sets and looping them again over the different models. And we're just outputting the test and train MSEs and finding out the gap. Let me just run real quick. So if we take a look at linear regression, decision tree, and neural network for the first data set A, which is a linear one, you can see that the gap is it's zero. And I mean, there's not much to look at here. It's a very structured data set. So this is, yeah. Where it kind of jumps up a lot when it comes to the gap with B, which is a polynomial plus some noise. You can see right here the gap is -18 and the gap is 6. And then when we try to run the neural network, it just stops at 3000 iterations. I'm not exactly sure why. I tried my hardest to lower the noise right here, but I don't know. It's a little weird. It's a little weird. I think I did something wrong, but yeah. I mean, it's stopping at 3000 iteration isn't too bad. I mean, this still should give us a good output and something to properly analyze. But you can see how the gap kind of jumps up a tad bit. But in my opinion, I think the best way to visualize the difference between the gaps between all the data sets is looking specifically at the decision tree. And you can see how right here we have 75 as opposed to B, which is only 6, right? And then after we train or we fit the models on each of the different data sets, we can move on to the compression. So right here, it's very simple. We're just using the OS zipping methods right here. And we can see right here that this is being measured in bytes. So you can see, actually, let's just jump here. This is very simple. You can see the original values of each of the data sets were very similar. They're all 38,000-ish. And after compressing them, right, we get for A, 7,000, around 8,000, let's say. B, 14,000. And then C, which is the highest, 20,000. Uh, so, yeah. Am I missing something? Yeah. Okay, okay. All right. So the generalization gap and the dataset complexity were found to be positively correlated, and the difference between training and testing performance rose as the dataset's complexity increased. To put it another way, models that were more complicated found it more difficult to identify consistent patterns that applied to new data, which resulted in a larger generalization gap. The simpler data sets are easier for models to learn from and generalize over, while more complex or random data sets make it considerably more difficult. So, in conclusion, the final takeaways should be that compression is a useful and simple way to estimate dataset complexity. Lower complexity datasets tend to lead to better generalization across all models, and high complexity datasets produce larger errors and larger generalization gaps. Overall, this entire research fully supports the hypothesis that simpler datasets are more learnable and that compression-based complexity estimations can give useful insights into model performance. That is about it. Thank you for listening.